So we're going to talk about um, the last laboratory or about the a fake finder. We are building an AI model that can easily classify image as AI generated or a fake one and real images. So we implement here the transfer learning. Instead of training from scratch, we use the transfer learning. We take a powerful pre-trained model like MobileNet V3 and it adapt it to our task. What is our task is to generate whether the model is fake or real. So the first step we did is we prepare the data. We load the data set. We create because they create the data set splits. We splits it. So we load the images using the image loader. Our data set is structured like we have the train and test folder, and inside of it contains a fake and real. So the image folder, when we import the image folders, it automatically reads folders. It assigns labels like fake is equal to 0 and real is equal to 1. So like for example, the codes is we import the image loader from Torque Vision, the datasets, we import the OS, and we have the function of create dataset splits. Inside of the parameter of it is data path. So we initialize the train dataset is equal to image folder, root equals os.path, and join data path like that. And we initialize all of the validation dataset accessing this image folder. And the return values of the create dataset splits functions is training datasets and validation datasets also. So next is we transformations. We define the transformations. Uh, in the neural networks, we expect the same image size, normalized values, more variety or augmentation. In training, we transform with augmentations. We add randomness, like improve generalization. Um, we use the transforms that compose inside of it. We random resize crop in the 224 pixels. We did transform the random horizontal flip. We transform color jitter and set its brightness and its contrast. Like in the brightness is 0.8 by 1.2, and also in the contrast is 0.8 and by 1.2. We transforms it to the tensor and we normalize it using the existing mean and standard deviation. Next is validation transform. Here in validations, we don't need randomness. Instead, we just resize it by 224. We transform it into the tensor so it could easily calculated, and we normalize it. And all of those things are assigned in transform that compose. So the final function is we call define transformations, and we set the mean is equivalent to image net mean in the parameters of that function, and the standard deviation is equivalent to image net STD. So we return values that train transformations and validation transform. So here is the data loaders. Data loaders, we call it create data loaders functions. So what it does is applies transformations with the batches of data, and we shuffles training data. So yeah, like for example, the codes is of course we import as always the data loader from Torque data, and we have the functions create data loaders. Inside of the parameters of this create data loaders is train set, validation set, and batch size. We initialize train transform and validate transforms into define transformations, because those define transformations return the values of train transform and validation transform. And we like an object of it like we train set the transform and val set the transform, and of course we shuffle it and the batch size, and create data loaders return values train loader and validation loader. Next is The part two is transfer learning. We load the pre-trained model, like load mobile net tree model. So the goal is to load the mobile net v3 and its weights. So the key concept here is the model architecture is not equivalent to weights, but we must load the weights manually. So here in this function, load mobile net v3 model functions. So the parameter of it is holding weights path, and we initialize the model, the architecture of mobile net v3 large, and we set the weights equivalent to none. Next is state the dictionary, or um, we load the weights path, and yeah, we must load the we load the weights manually. This is dark load. Inside the weight paths, where is the weights and location, target the device inside the CPU, and we load it. We're using the model that load state and the city state, and it returns the model. Next is modify last layer. So we use the functions update model last layer. So when we modify the last layers, use the original model output is thousands of classes in the ImageNet, but we only need two classes, which is fake versus real. So the steps here is we freeze the feature layers using this loop, like param in model that features and parameters, and we turn off the gradients calculations, like param that requires grades equivalent to false. This prevents destroying learned knowledge. We replace the classifier. We import the torch.nn as nn, and we have this functions update model as layer, and so the parameter of it is model and num process. And of course, we also turn off the gradients calculations, and to access the the classifier input features in the model is we use the model the classifier inside of the index initial index of it is -1 to find its last. And to access this, we just add the dot in features. So we set the new classifier. Of course, is we have the input features. We use the and linear, and the input feature is still the same, the input features, but what does not the same is the number of classes. And yeah, it returns the model. Part 3 is we train it. We have the loss functions like cross entropy loss, it's used for classification problems, and we did the optimizer. We only updates the new classifier layer, like only the gradients that is active. And we have the training loop, like helper utils the training loop. Inside of it, we did the forward pass, compute loss, backpropagation, update weights, and validate check. Next is visualization. We show the predictions in the helper utils to visualize predictions. It shows images, predicted labels, and true labels. We test it on no image. We use the helper utils to make predictions. Our model becomes usable like a real AI tool. So, summarize with the concept that we need to understand is transfer learning is instead of learning from scratch, we use the pre-trained knowledge. We only adjust the final layer. The freezing layers is it prevents the unlearning of useful path features, and it usually codes like param that requires is given the false. Next is data augmentation makes models stronger by flipping, cropping, changing brightness, and why we choose the mobile net v3 because it's lightweight, fast, and high accuracy. So we build a full pipeline here. From the load data set, we apply transformations, create data loaders, load pre-trained model, replace the last layer, train model, visualize results. So on our previous model, that is 70% accuracy after tuning. And after tuning this model, it becomes better performance with less effort. This is what's the powerful of transfer learning.